Hello, welcome to Special Relativity Part 3. Let's continue and examine how different coordinate systems see other coordinate systems. Here we have Alice and Bob, and both of their world lines go through this point, so they can agree about it, and we will use it as the 0, 0 point of both coordinate systems. Now Alice and Bob use the same procedure with the same tools, with the same clock and the same stick, and get their coordinate system. So here we have 1 unit of time of Alice, 1 unit of distance of Alice, 1 unit of time of Bob, and 1 unit of distance of Bob. According to their definition, the speed of information is 1. It travels 1 unit of distance over 1 unit of time. And the same for Bob. It travels 1 unit of distance over 1 unit of time. Now in Alice's eyes, Bob has a speed moving away from her. And by that I mean that using her coordinate system, she can tell what this speed is of Bob moving away from her. And in the eyes of Bob, Alice has a speed moving away from him. And he can determine the value of the speed according to his coordinate system, and we will get the same speed. So Alice sees Bob moving away from her at a certain speed, and Bob sees Alice moving away from him at the same speed. Now let's see how they see each other's coordinate systems. Let's start with how Bob sees Alice's 1 second. So this is Alice's 1 second, and we go along a parallel line to Bob's space. These are the lines of the coordinate system of Bob, and we see that Bob sees Alice's 1 second as happening after 2 seconds of his. So this is 1 second of Bob, and this is how he sees Alice's 1 second as happening after 2 seconds of his. And the other way around, how Alice sees Bob's 1 second. So this is Bob's 1 second. We go along a coordinate line of Alice, which is parallel to Alice's space over here at time 0. And we see that Alice sees Bob's 1 second as taking 2 seconds of hers. 1, 2. So as we said, Alice and Bob see each other's coordinate systems in the same way as the other coordinate system second happening after 2 seconds of their own. Now let's keep these markings in place and say that Bob is moving at a higher speed compared to Alice. Now let's see what happened to how they see each other's coordinate systems. We start with how Alice sees Bob's 1 second. This is Bob's 1 second now. And we go along a parallel line to Alice's space at time 0. And we see that now Alice sees Bob's 1 second as happening after about 4 seconds of hers. So now Alice sees a bigger discrepancy between her 1 second and Bob's 1 second. Now it's a little bit harder to see for Bob because we moved his world line, but if we bring back our old 1 second and how Bob saw Alice's 1 second, so this was the difference between them. And now the difference is between this 1 second and where this line hits Bob's world line. And although we can't see it, it will be the same as the difference between Alice's view of the old situation and her view of the new situation. As we saw, everything is symmetrical between Alice and Bob. They see each other's coordinate systems in the same way. To summarize this, we see that the higher the speed between the two world lines, the bigger the difference in how they see the other coordinate system units. At zero speed between the world lines, when the world lines are parallel, one coordinate system sees the units of the other coordinate system as equal to its own. Two world lines that have no speed between them and use the same procedures and the same tools, the same clocks and the same sticks for their calibration, will have the same coordinates systems. They may call the point 0, 0 a different point, but the coordinate systems themselves will be the same. And if we follow the mathematical equations of the transformation, then we see that at the speed of information between the world lines, so if one of the world lines is along an information track, one coordinate system sees the units of the other coordinate system as infinite. The coordinate system of the world line that is along an information track is compressed to one line. And therefore, any other world line sees an infinite amount of seconds going by in one point on its world line. And in the intermediate speeds, one coordinate system sees the units of the other coordinate system as bigger than its own. So 1 second of the other coordinate system takes more than our own 1 second. And how much this difference is according to the speed between the two world lines. And again, if we look to the mathematics, we can see that the difference is pretty small up to a very high speed between the two world lines. So only when the speed between the two world lines is a significant amount compared to the speed of information, then the differences between their coordinate systems start to be noticeable. And when the speed between the two world lines gets close to the speed of information, suddenly the differences grow bigger and bigger very quickly. Now, it could be a little bit confusing looking from our outside perspective, but the relationship is true between any two world lines. So if we look from Alice's point of view and we look at Bob, it has a certain speed in Alice's coordinate system, and accordingly, Bob's 1 second looks like 2 seconds for Alice. Now if we look at Bob and Jack, and we look from Bob's point of view, Jack has a certain speed moving away from Bob in Bob's coordinate system. And the speed between Bob and Jack is the same as the speed between Alice and Bob. Even though it looks like there are totally different speeds, this is a very small angle between the world lines, and this is a bigger angle between the world lines. But as we said, the absolute value of the angle is not the speed value itself. It depends on the coordinate system in which we are looking at. So from our outside view, it looks like Bob and Jack are in a different situation than Alice and Bob. But if we look at Bob from Alice's coordinate system and we look at Jack from Bob's coordinate system, they are in the same situation. And accordingly, Bob will see Jack's 1 second as double of its 1 second. So because the relationship between Bob and Jack is the same as the relationship between Alice and Bob, they will see the other coordinate system in the same way, even if it looks like their situation is different from our outside perspective. And again, for Jack, there is the full range of world lines between it and the information track because with Jack's coordinate system, every small change in the angle changes more of the speed compared to Alice's same change in angle. So the view from our outside perspective of reality, things that exist, is misleading compared to the coordinate system view. And this is because coordinate systems do not exist. The lines that comprise a coordinate system do not exist in reality. The coordinate systems are a construction, but they are the systems that we deal with in physics. And special relativity tells us how to move from one coordinate system to the other. Now, the geometry of reality is normal. Our model is a two-dimensional flat surface, and actual reality is a four-dimensional flat structure, and it obeys the geometry rules that we normally use and seem intuitive to us. These are the rules of Euclidean geometry. And I say this because you may hear of the geometry of special relativity, which is called hyperbolic geometry. This geometry, the hyperbolic geometry, is the normal geometry viewed from a perspective that has time. So the hyperbolic geometry that can be used in limited separate regions of reality is because of the definition of time and us using the lens of time to exist in reality. So we view reality through actual world experience, and because of this way of viewing reality, our geometry is hyperbolic geometry. And by that I mean that the hyperbolic geometry describes the transformation between coordinate systems. If we look at our model, it is depicted on a two-dimensional flat screen. And if we look at any line over here and we measure it from our outside perspective with a ruler or our own outside perspective coordinate system, then all the lines, and if we have triangles over here and angles, will obey the normal geometry that we know, Euclidean geometry, and it will look to us like they behave in an intuitive way. But once we take into account our actual world experience of this reality and the way it forces us to construct coordinate systems from within, from our inside perspective, then we get that 1 second of Alice and 1 second of Jill and 1 second of Bob are not on a same straight line. The line that connects all the 1 second values of all the world lines, straight world lines, is this black line over here, which is a hyperbola. It continues on the other side in a symmetric way. So the line of 1 second is a hyperbola and not a straight line. But again, this is the line that describes the transformation between the different 1 second coordinate of different world lines. The 1 second of Alice is a straight line that is parallel to its 0 line that is parallel to its 2 second line, and the same for Jill and for Bob. Their 1 unit of time is a line that is parallel to, in this case, Jill's space. So the coordinate system is over here, and the next one is over here. And the same for Bob. The coordinate, the simultaneity line of 1 second of Bob, all the points that are 1 second according to Bob, are on a straight line. They're not on a hyperbolic line. They're on a straight line that is parallel to Bob's space at point 0. So the hyperbolic line is a manifestation of the transformation between different coordinate systems that are created in our actual world experience view. And because this is the view that we live in, this geometry is useful to us. It's the geometry that we live in. The geometry that we do not see, because we do not have the ability to step out of reality and look at reality from outside, like we do with this model. So this geometry is the Euclidean geometry, the geometry that is intuitive to us. This is very strange. Why the geometry that is intuitive to us is the one that we do not see, and the geometry that we live in is the one that seems strange to us. And the reason is that the scale of behavior is important. So the differences in clocks and distances is negligible in our day-to-day environment. The relationship between world lines in our day-to-day life is such that we can all use one coordinate system that is accurate enough for all things. In our own experience, we do not notice the effects of the existing differences between coordinate systems. So even though we live in the hyperbolic geometry, because in our day-to-day life we have a certain environment, this environment is very close to an Euclidean geometry. And our intuition is created according to our day-to-day life. And that's why Euclidean geometry is more intuitive to us than the actual hyperbolic geometry that we just do not notice in our day-to-day environment. So our day-to-day environment is more like this. Alice, Jill, and Bob's world lines are very close to parallel to each other, and therefore all have the same coordinate system. In fact, with the resolution that we have in our depiction over here, I have to draw Alice, Jill, and Bob's line as parallel lines because within our day-to-day experience, the deviation from these lines being absolutely parallel is so small that I cannot depict it. For example, if we look at Bob over here and we change the world line to this world line that has a small angle between him and Jill and Alice, this small angle is a representative of Bob moving away from Jill and Alice at about a speed of 20 million kilometers per hour. So about 10,000 times faster than a fighter jet, that it is about 2,000 kilometers per hour. And that is probably one of the fastest things that we see in our day-to-day life. So even this small change in the angle between Bob, Jill, and Alice is not realistic for our day-to-day life. Another important thing to point out is that this depiction is just an extremely small, tiny part of the reality described by all the depictions so far. For example, if we look to Alice over here and her coordinate system, then the entire line from this point up to this point is just a few nanoseconds. Nano means 1 second divided by a billion. With this extreme zoom in, the distances between Alice, Jill, and Bob are on the scale of our life environment. Now let's look at this statement. The speed of light is a limit. And by the speed of light, we mean the speed of information. The speed of information was first identified as the speed of light, and therefore this is the terminology that we use in physics. The speed of information is the speed of light. So if world lines start in a relationship of less than the speed of information, the speed of light, then the speed of light is a limit between them. This is because the information tracks are the directions in which the desire to change the world line's trajectory work. And so the maximum is for this desire to be fully achieved and the world line's trajectory to merge with the trajectory of the information track. And even this never happens because an elementary particle or a thing has mass. And mass has the desire to keep the world line's trajectory straight. And that will always prevent the desire of changing the world line trajectory to the information track from achieving its absolute goal. Here we have Bob, Alice, and Jill. And here are some information tracks. If these world lines start with a speed between them that is less than the speed of information, the speed of light, then the speed of light is a limit. And in our case, we decided that the information tracks that exist in reality are the lines that are a 45-degree angle with our perspective. So as long as all the world lines are at a smaller angle than 45 degrees compared to our perspective of reality, then the speed between them cannot grow bigger than the speed of light, the speed of information. The reason is that if we look at Jill over here, and let's say that at this point, this information track has a field and it wants to change Jill's trajectory to go along its information track. And again, let's imagine that this field is absolutely successful in its desire and it changes Jill's trajectory in this manner over here. Then the next field, the next information track, will be parallel to Jill's new trajectory and will never affect Jill's world line. It could not change Jill's world line at this point because it does not hit it. The only field that can affect the world line of Jill at this point over here is an information track coming from this side, and it wants to change Jill's trajectory either in this direction or along the same trajectory that it is already on, so it will not change anything. And if it changes the trajectory of Jill's world line in this direction, then the speed between Jill's world line and Alice and Bob will again be smaller than the information speed, the speed of light. So in this scenario of special relativity, a reality without gravity, and with world lines that start with the speed between them that is less than the speed of light, the speed of light will be a limit that cannot be achieved. So the speed between elementary particles or things has to be smaller than the speed of light, the speed of information. Now let's look at this statement. A clock that changes its trajectory is transformed, meaning it becomes a new clock. The old clock sees the new clock is running slow, and the new clock sees the old clock is running slow. Here we have Jill, and Jill moves on a straight world line up to this point, and at this point she changes her trajectory to this straight world line. Now to change from one straight world line to another, we need to move through a non-straight world line, which means acceleration. So another way to say this is that Jill experienced acceleration. However, in this case, we assume an unrealistic situation where the acceleration is infinite and the change in trajectory happens over a point and not over a non-straight world line. And this is only to illustrate our subject. Jill starts measuring her time over here and decides this is point 0, so this is the zero simultaneity line. and this is the one simultaneity line. And this point where the trajectory changes is 2 seconds after Jill started measuring her time. Now the clock changes its trajectory with Jill, meaning the simultaneity lines change to this direction and the time interval changes to this time interval. So this is a difference of 1 second from this point on, and this is the difference of 1 second in the old world line. These changes happen according to what we described in our videos in a way that will keep the speed of information the same in both coordinate systems. So even though Jill has the same clock with her through this transformation, this clock is in effect two clocks. The clock itself goes through transformation, and we can treat it as being two different clocks, one before the change in trajectory and one after the change of trajectory. So every point along this simultaneity line number 3 over here will be 3 seconds after Jill started measuring her time, and every point on this 4 simultaneity line will be 4 seconds after Jill started measuring her time. Now let's imagine that Jill did not change her trajectory, which means the simultaneity lines and the time interval of 1 second remain the same. And this would be the simultaneity line of second 3, and this would be the simultaneity line of second 4, and this would be the simultaneity line of second 5. Now if we look from our new clock, this is second number 4, and this is the simultaneity line for second number 4, meaning this point over here is 4 seconds from the 0 point where Jill started measuring her time. But if we would stay with the old clock, then 4 seconds would only pass at this point over here. So with our new clock, if we look at our old clock, it is running slow. 4 seconds would only pass over here, when for Jill in her new trajectory, 4 seconds already passed over here. And the same goes to the other direction. From the point of view of the old clock, this is 4 seconds, which means this point over here is 4 seconds from the 0 time where Jill started measuring her time. But the new clock sees 4 seconds only at this point over here. So from the point of view of the old clock, the new clock is running slow. Only over here, 4 seconds pass when they actually passed over here for the old clock. The important thing to notice is that the same clock that stayed with Jill goes through a transformation when its trajectory changes, when it experiences acceleration at one point or another. And this is also true for Jill. When Jill goes through a trajectory change, she is transformed. So time and space are a calibration of ongoing change. And ongoing change is how we see reality. That is our actual world experience. And this means that the phenomena we showed for clocks and distances apply to all things. If we view a clock as running slow in our coordinate system, which is the coordinate system of our world line, then all the things that are moving with this clock will act slowly in our eyes. So even though I said that coordinate systems do not exist, because we see reality through actual world experience, we view reality in the same way as coordinate systems. Coordinate systems are just a reliable, precise way for dealing with the phenomena of seeing reality by actual world experience. meaning that coordinate systems are comparable. We can put them one against the other. Coordinate systems are a tool for changing our experiences into scientific observations that can be used to discover the rules of reality. They describe our experience. So special relativity, which is the theory that tells us how coordinate systems relate to each other, is the theory that describes our experience of reality. Okay, with that we end our chapter of special relativity, which was the theory that brought a major change into the concepts of time, space, and reality. But as we mentioned, special relativity is a reality without gravity. And gravity is part of our actual world. In the next videos, we will introduce gravity into this described reality and see how it changes it, and get a feeling for some of the consequences of this new description of reality that includes gravity.